Good afternoon, everyone. My name is Arghadip Lashkar. I am an assistant professor in the Department of Civil Engineering at IIT Bombay, and I will be offering this topic on deflection of statically determinate structures, which will be basically consisting of 3 sessions. Uh, in this topic, I would mainly deal with the calculation of deflections of structures under which are statically determinate. There are indeterminate structures whose deflections can also be calculated, but in my talk, mostly the deflections of statically determinate structures would be covered. If I look at the contents of my talk, I would first start with an introduction about the necessity of calculating deflections, why we need to calculate deflections. And some of the methods that I will cover are shown on this slide. You can see that I'll be talking about the double integration method, the Macaulay's method, which is basically a special case of a double integration method. Then I'll talk about moment area theorems, conjugate beam method, and finally I will talk about two energy methods which are based on the principles of conservation of energy. One is the virtual work method and the second one is the Castigliano's theorem. Now, for today's lecture, I'll first talk about the introduction and the elastic beam theory based on which the double integration method, the moment area theorem, and the conjugate beam methods have been developed. So in today's lecture, I would cover double integration method and Macaulay's method. I would like to have the questioning after a session of the talk. So what I would do is I would first cover up to the double integration method, and then I would open the session for questioning for all the participants. And then I would take maybe like a 5-minute break. And at the end, I would cover the Macaulay's method. In the lecture on 26th of February, I would cover the moment area theorems and conjugate beam method. And finally, on 4th of March, I would cover the energy methods. Now, moving on with the introduction of this topic. So first of all, why do we need to calculate structural deflections? Most often when we design structures, we have the first thing that comes into our mind is the strength of the structure, whether it is adequate. But in addition to paying attention to the strength of structures, it is also important to calculate the deflections. And there are various reasons for which the deflections can occur in structures. Main thing is due to the loads, the structures will deflect because no structure is practically or completely rigid. And in addition to the loads, deflections might be due to temperature changes in the structural members or due to some fabrication errors or due to settlement of the structural supports. So these are the various reasons due to which the structure might undergo deflections. And in order to ensure that our structure is stable and the integrity of the structure is maintained, we need to be able to calculate the deflections of these structures. Now, there are various other reasons for which we need to calculate for deflections of structures. There are a number of structural materials such as concrete, which are mostly used for civil engineering structures, are brittle, and hence they fail without giving much warning. Hence, it is necessary to prevent the damage of these materials, and in order to do that, it is also necessary to calculate the deflection of such structures. Regarding the serviceability, you need to avoid excessive deflections and vibrations in structures because it will render or make the occupants of those structures or users of those structures unsafe. And finally, as I said, there are indeterminate structures whose deflections and analysis will not be covered in this lectures, but we can calculate the forces or internal forces in these indeterminate structures by calculating the deflection of the statically determinate structures, which is a precondition for analysis of indeterminate structures. Now, before I go ahead further, I would like to just point out that in this topic, that all the deflection calculations will be limited to structures which have linear elastic material response. When I say that, I mean that if you unload the structure, it will, excuse me, it will return to their original undeformed position. And also, if there are two different sources of load or deformation, then the total deformation of the structures can be calculated by calculating the individual deflections due to the individual loads. In other words, what I mean is the principle of superposition is applicable. Now, in order to calculate the deflections in structures or displacement or rotations in structures, we need to be familiar with the various kind of supports that these structures have. So some of the typical support conditions that are encountered in the common civil engineering structures are shown on this slide. The first one is like a roller or rocker support, which basically restrains the movement or displacement of the structure in only one direction, that is perpendicular in the direction perpendicular to the support. The second one you see here is on this slide is a pin support, which basically restrains the displacement of that structure at that point in all three directions. The third support condition that we most commonly encounter in civil engineering structures is called a fixed support, which restrains the displacement as well as rotations at those supports. And the fourth one you see here, fixed joint connection, which is normally common in a frame member. And what in this fixed joint connections, the rotation of the two members which are connected at those joints are equal. In other words, the displacement at those joints or the rotation at those joints are allowed, but the rotations of those two members are equal. Finally, the last connection that we encounter in civil engineering structures are the pin connected joints. And in this kind of joints, the members are independent to move irrespective of the rotation or deformation of the other member. The two members which are connected are free to move by themselves. Now, before I start with the first method of calculating deflection, I would like to give a small background about the elastic beam theory based on which the first method, that is the double integration method, is developed. So I'm sure that if you all have taken any classes on strength of materials or solid mechanics, you all have been familiar with this elastic beam theory, but I'll quickly recap. So if you have any a structural beam that is shown on this slide, you can see that there are different kinds of internal forces that develop in that beam due to the external loads. Now, the three most common types of internal loads that develop are the axial force, the shear force, and the bending moment. Now, deformations in a structural member can occur due to all three of these internal forces. However, it has been noticed that for members like structural beams, where the span to depth ratio is much higher, in other words, the length is much greater than the depth, the deflections are primarily caused due to the bending internal forces or the internal bending moments. Now, in order to be able to calculate the deformations, we need to find a relationship between the forces and the deformations of the structure. So what we have done here is we have taken this beam and we have taken the x direction, we have to have towards the right. So it starts from this point A and the x distance is measured along the span of the beam towards the right. The deflection of this beam is measured in the vertical direction. So any deflection which is upwards is measured as a positive vertical deflection. Now, due to the action of these internal loads, applied loads, there will be internal moments that develop in the beam. So in order to correlate that internal moment with the deformation, what we have done here is we have taken a small section of the beam which is having a length dx, and we have separated it out here. Now, initially it's a prismatic section, so as you go over the depth of that section, the length is dx. Now, once this beam is subjected to the external loads and it bends, it will be subjected to some internal moments m, and it will deform, because of which it will have a deformed shape like this. Now, in this case, at a distance y from the center or the neutral axis of the beam in this case, the length of that element would reduce. So if you want to find the strain in that element, it is given by this expression that you see here, which is rho minus y d theta minus rho d theta over rho d theta. Now here rho minus y d theta is the deformed length of that element, where rho is the radius of curvature of this element, y is the distance of that section we are considering from the neutral axis, and d theta is the angle that is formed at the center of this curved element. So that is the strain in that element. So rho minus y d theta is basically the deformed length of that element, and the initial length of that element is the same as the length at the neutral axis, which is rho d theta. So that is the increase in length, and that divided by the original length gives you the strain. So this basically gives you a relationship between the radius of curvature of that deformed element and the strain. Now, if you recall your solid mechanics principles, you know that the stress in that element would be given by this term my by I, where y is the distance from the neutral axis. So now if you combine this stress and the strain in this relationship, which is the relationship of stress and strain using the Young's modulus for a linear material, you get the 1 by rho is equal to m over EI. So this is the relationship between the radius of curvature of that deformed element and the internal bending moment which develops in that element due to the applied loads. So once again, if we look back at that relationship, 1 by rho is equal to m by EI. Now again, this relationship, this dx is the length of that or the width of that element, and that can be written as the radius of curvature times d theta. So here what we have done is we have replaced this 1 by rho by d theta by dx, and we have taken this dx to the other side. So what you get is d theta by m over EI into dx. Now if you remember from your geometry learnt in class 12, the radius of curvature is given by this relationship, which is the second derivative of v with respect to x over 1 plus dv dx square whole to the power 3 by 2. Now in this study, what we are considering is small deformations. In other words, the rotation is where dv dx is basically the rotation of that beam element. Now for small rotations, this term dv dx square is much less than 1. Or in other words, we can say 1 plus dv dx whole square is almost equal to 1. So we can say that 1 by rho is equal to dv dx square. So when we substitute this here, instead of 1 by rho, we write dv dx square. We can say m by EI is equal to dv dx square. So this basically relates the internal moment that develops due to these applied loads with the deformation, that is the term v in this equation. Now remember, this is the basic equation that will be used to develop the three methods that I'll discuss, that is the double integration method, the moment area theorem, as well as the conjugate beam method. So in all these three methods, you will be this will be the starting point. Now just keep in mind that since we will be using this equation, there are certain assumptions that we have made in order to derive this equation, and these are the assumptions. So first of all, there is no horizontal displacement along the elastic curve. By this I mean that if you apply these loads, this beam is deflected in vertical direction, but it does not deflect in the horizontal direction. The beam deflections occurs only due to bending. So there might be axial forces and shear forces also in the beam, but we neglect the deformations due to those axial forces and shear forces in the beam. The beam material is homogeneous. In other words, this E is constant and it is linear. So it means that it is once you remove the loads, it can go back to the original condition, and also the principle of superposition is valid. And last but not the least, just keep it in mind that this equation is valid for small deflections, because we have neglected this term 1 dv dx whole square when we have substituted this equation in the top equation. So now we come to the double integration method, which is the first method for calculating deflection of structural members that I will discuss today. So as I mentioned, this is the starting point of this equation is this the relationship, the second order deformation equation that we developed, that we saw in the previous slide. So m by EI is dv dx is equal to the second derivative of the displacement with respect to the distance along the length of the beam. Now if you integrate both sides of this equation, you get dv dx is equal to m by EI. But now here dv dx is the slope of that beam at any section. If you integrate both sides of this second equation, you get v. So integration of dv dx is v, and you get double integration m by di. So this is the basic uh, principle in this method, where you basically integrate the m by ei function of the beam twice to get the deflection and once to get the slope at any section. So here theta is the slope of that elastic curve of the beam. Theta is the slope of the elastic curve of the beam at any section, and v is the deflection. Now, before I proceed further, I'd just like to draw your attention to the sign convention that we used in this method for specifying excuse me, the theta and the v. So in this case, for the beam, we considered the distance towards the right as the positive x direction, and we considered the deflection in the upward direction as the positive deflection v. Now for the rotation, if it is counterclockwise, in other words, if it is in the for a positive x direction, if the deflection is towards the positive v, then that rotation is positive. It is considered a positive rotation. So this is the sign convention for the positive rotation, and this is the sign for the vertically upward direction is the sign for the and the vertically upward direction is the sign for the positive deflection. Now coming back to that equation for this elastic curve, which is basically the deflected profile of the beam. We all know that if we integrate this moment function of the beam, which is basically expression in terms of x, where x is the distance from one end of the beam, what we get is we'll be getting some constant of integration on the right hand side. So those constant of integration have to be evaluated in order to be able to calculate the deflection of the beam at any section, or in order to get the equation of that elastic curve. So the elastic curve calculated using this double integration method will have the two constants of integration. Now in order to determine constant of integration, what we need to do is we have to provide the values of either v or theta at some known points on the beam. In other words, those are known as the boundary conditions. Now beams with discontinuous loads will have multiple functions which are valid within the range of discontinuities, and the continuity conditions in that case must be used to evaluate the integration constant in the elastic curves of adjacent discontinuities. So I'll have two examples which I'll be showing after this. So once we go through those two examples, these four sentences would be a lot more clear. So this is the first example that I want to discuss with you. It has a simply supported beam, and it is subjected to an external moment m0 at one of its ends. And what it is saying is, for the beam loaded as shown in the figure below, determine the equation of the elastic curve using the double integration method. And they're also asking, determine the values of the maximum deflection and maximum slope of the beam, and the locations at which the maximum deflection and the maximum slope will occur. Now, one of the prerequisites for this course, for this talk, was the students or the audience should be familiar with the bending moment diagrams and shear force diagrams and axial force diagrams of structures. So, if any structure is given and any loading is given, you should be able to draw the bending moment, shear force diagrams, and axial force diagrams. So we'll start ahead with the solution. We'll go ahead with the solution of this problem. And what we see is, if you draw the bending moment diagram of this beam, this is what it will look like. It will have a moment of m0 at the end A. At the end B, which is a roller support, it is having zero moment. So this is the bending moment diagram, and the moment function of that beam, that is the moment at any distance x from the left end, is given by this equation m0 1 minus x by L. Now in order to calculate the equation of the elastic curve, that is the displacement function of this beam at a distance x, what we have to do is, by the double integration method, we'll write d2v dx square is equal to m by ei, and instead of m, we'll replace it by this term m0 1 minus x over L. Now if you integrate both sides of this equation, you get dv dx on the left hand side, and on the right hand side you will get m0 by ei x minus x square by 2L, plus there will be a constant of integration c1. If you integrate it one more time, you will get v is equal to m0 by ei x square minus 2 minus x's cubed by 6l plus c1x plus c2. So these are the two constant of integration that I was talking about in the previous slide. So whenever you try to solve the equation, the deflection function of, or try to get the deflection function of a beam using the double integration methods, you will always encounter these constant of integration which you have to solve using the boundary conditions. Now for the boundary condition of this beam, it was a simply supported beam, so the deflections at both ends should be 0. So at x is equal to 0, the deflection, that is v, is equal to 0. If you put in this equation, the last equation that you see here, if you put v is equal to 0 at x equal to 0, put x equal to 0 here, you will get C2 is equal to 0. The second boundary condition for this beam was at the other end, that is at the end B, the deflection is 0. So if you put x is equal to L, at x equal to L, v is equal to 0. So if you come back again to this equation, you put x equal to L here on the right hand side and you put the value of v is equal to 0. And if you solve it, you will get C1 is equal to minus m0L over 3EI. Next, what you do is you put the values of these constant of integration that you obtained using the boundary conditions back into these equations. So if you do that, what you get is v is equal to m0 by 6EI, x square minus 2 minus x cubed by 6L minus Lx by 3. So this Lx by 3 is coming from this term ml by 3EI. So that m0 by 3EI has been taken as common, and so you are left with Lx by 3 in the brackets. Also similarly, if you put the value of C1 here, you will get dv dx is equal to m0 by ei x minus x square by 2l minus l by 3. So now this is the equation for the deflection of the beam at any distance x from the left end, and this is the equation for the slope of the beam at any distance x from the left end. Now this is the first part of the problem. They had also asked you to calculate the maximum slope and the maximum deflection of that beam. Now since we have the equation for the elastic curve of the beam that is given here, v is equal to m0 by ei x square minus 2 minus x cubed by 6l minus lx by 3, what we can do is, in order to find the location at which the maximum deflection occurs, we just take the derivative of this. In other words, we take the expression on the right hand, dv dx is equal to this, we equate this to 0. So the point at which the maximum deflection occurs, at that point within the span of the beam, normally the dv dx, that is the slope of the beam, is equal to 0. So we have to find the location at which the slope of that beam is 0. So that is what we have done here in this slide. So in order to determine the location at which the maximum deflection occurs, obtain the value of x at which the first derivative of the elastic curve equation is equal to 0. So take this equation of the elastic of the first derivative of the elastic curve and equate it to 0. So that will basically give you this expression x minus x square by 2l minus l by 3 is equal to 0. If you solve this, you will get, this is a quadratic equation, you will get two values of x. One is x is equal to 0.422l and the other one is 1.56l. That value of x is within the range of 0 to l. So x cannot be 1.56l. In other words, what I'm saying is this equation of this elastic curve will have either a maximum or minimum value at 1.56l, but in our case, for the case of this problem that we are solving, this is not applicable because it is not within the range of applicable values of x. So at x equal to 0.422l is the location at which the maximum deflection will occur. So next what you do is you have to obtain the maximum deflection. So what you do is you come back to this equation for the and you put x is equal to 0.422l in that equation. If you put that and you solve it, you will end up with minus 0.064 m0l square by ei. Now this minus indicates that this is in the vertical downward direction. Remember when I talked about the sign convention for deflection? Deflection in the vertically upward direction is positive. So once it comes out negative, that means it is in the vertically downward direction. So that is about the deflection, maximum deflection of the beam. It is minus 0.064 m0 L square by EI. So minus indicates it's in the downward direction, and this maximum deflection will occur at a distance of 0.422 L from the left end of the beam. Now for the maximum slope, what we do is we take the derivative of this v dx, we take the double derivative. So it is d2v dx square. So if you equate that, if you equate the second derivative to 0, you will get x is equal to L. Now if you put x is equal to L in this equation, you get the slope is m0 L by 6EI. So that is the slope at the beam at x equal to L. But there is one thing that you should be careful about, which I will now talk about, that this is one of the drawbacks of the double integration method. You always cannot take the higher order derivative and equate it to 0 and get the location of the maximum slope or deflection. In this case, what you get a positive rotation at the right end, that is at x is equal to L, and that is m0 L by 6EI. However, if you come back to this equation for the slope of the beam, which is dv dx equal to m0 by EI x minus x square by 2L minus x by L. In this equation, if you put x is equal to 0, that means at the end A of the beam, you will see that the dv dx at x equal to 0 is minus m0 L by 3EI. So what does this indicate? This indicates that at this end, it is having a negative slope. That means it is in the clockwise direction at this. And notice that the magnitude of this slope at this left end is higher than the magnitude of the slope at the right end. So this is basically to remind you or to show you that you should always calculate the deflection at the support condition in addition to the deflections or rotations that you get from the equation of the stick curve. In order to calculate the maximum deflection, in addition to taking the higher order derivative equal to 0, you should also pay attention to the deflections at the. So in this case, the maximum rotation of the beam will be at the left end, which is minus m0 L by 3I, and here the minus indicates it is in the clockwise direction. So just to stress on that point, the maximum positive slope of the beam occurs at x equal to L. However, the maximum negative slope of the beam occurs at x equal to 0, which is not obtained by equating the second derivative of the elastic curve equation to 0. In this case, the maximum absolute value of the slope is at x equal to 0. So at x equal to A, the value of the slope is m0 L by 3EI in the clockwise direction, and that's the maximum slope of the beam in this case. So this is the first example that I wanted to discuss, and there is one more example that I want to discuss, and this is for this cantilever beam, which is fixed at one end and free at the other. It is subjected to a concentrated load at a distance A from the free end, and they are telling you that beam is loaded as shown in the figure below. Determine the equation of the elastic curve using the double integration method, and also determine the values of the maximum deflection and maximum slope of the beam and their locations. Now in this case, you see that if you draw the bending moment diagram of the beam, this is what it will look like. At the fixed end, the moment is minus PO times L minus A. And at distance of L minus A from the left end, the moment is 0. And beyond that, the moment remains constant. So this is the bending moment diagram. So now here notice that the bending moment, if you write the moment function, it will have two equations. For x between 0 to L minus A, it is minus P into L minus A minus x. And when x is greater than L minus A and less than L, the moment is equal to 0. Now, to solve for the elastic curve of this beam using the double integration method, there are two sets of moment functions that we have to consider. One is valid for x greater than 0 and less than L minus A, and the other one for x greater than L minus A and less than L. So if you, I'm sorry, I just missed one slide which, yes, so these are the two equations of the moment function. One is valid for x greater than 0 and less than L minus a, and the other one valid for x greater than L minus a and less than L. Now if you come to this first equation and you use the double integration method, you can again write d2v dx square is equal to minus p L minus a minus x over ei. Now if you perform double integration, you get dv by, if you integrate it for the first time, you get dv dx is equal to minus p L minus a x plus px square by 2 plus this constant of integration c1. To integrate both sides again, you get v is equal to 1 by ai minus p L minus a into x square by 2 plus px cube by 6. Now again you get plus c1x plus c2x. Now what are the boundary conditions that you need to be able to solve these constant of integration? These are the boundary conditions at x is equal to 0. This is a fixed end. So at x is equal to 0, the deflection is 0 and the slope is 0. So the two boundary conditions you get here. So you get at x is equal to 0, v is equal to 0. If you put that here, put x equal to 0 here on the right hand side and put v equal to 0, you will be getting c2 is equal to 0. The second boundary condition is at x is equal to 0, that is at this left end, dv dx is equal to 0. So you come to this equation, you put x equal to 0 here, x equal to 0 here, and on the left hand side dv dx is 0. So that will give you c1 is also equal to 0. So if you put the values of constant of integration, which are basically 0 here, you will get the equations as v is equal to 1 by ei minus p L minus a x square by 2 plus px cube by 6. And also the slope of the elastic curve is given as dv dx is equal to 1 by ei minus p L minus a x plus px square by 2. So this is the equation. So the equation of the deflection and slope of the beam for x greater than 0 and less than L minus a. So what about the portion of the beam which is beyond this point, which is at x is equal to L minus a? For that, we have to solve this equation, the second order equation for the second moment equation, which is basically mx is equal to 0. Now, in order to solve this, if you have to get two boundary conditions to solve the two constant of integration, and those two boundary conditions are obtained from the equation of the elastic curve for the first part, which is at x is equal to L minus a. So what you do is, in this equation, put x is equal to L minus a and calculate the slope of the beam at L minus a. So this is the slope of the beam, minus p L minus a whole cube 3 by ei. And I'm sorry, this is the deflection, and the slope of the beam at x is equal to L minus a is minus p L minus a whole square by 2 ei. So this will be the two boundary conditions that we will use to calculate the constant of integration for this portion of the beam, which is between L minus a and L. So this is where we are solving the equations for the second part of the beam, which is d2v dx square is equal to 0. For this second part, mx is equal to 0. So if you just integrate it twice, you get, first you get dv dx is equal to c1, and then you get v is equal to c1x plus c2. Now, in order to solve this two constant of integration, we'll use these boundary conditions. The boundary conditions are at x equal to L minus a, the dv dx is minus p L minus a square by 2 ei. This is what we got from the previous slide. And also at x is equal to L minus a, the deflection is minus p L minus a cube by 3 ei. So these are the two boundary conditions that we are using to solve the constant of integration for the second part of the beam. So if you put those constant of integration back into the equation, you will get v is equal to, instead of c1, you will get minus P L minus A square by 2EI x plus P C2 is P into L minus A whole cube by 6EI. And also the slope of the elastic curve of that beam is given as dV dx is equal to C1. So C1 is minus P L minus A square by 2EI. So this is the equation of the slope and deflection for the portion of the beam in this region, which so this slide is basically summarizing the slope and deflection equations for both regions of the beam. So this is for the first part of the beam, which is between 0 to L minus A, and this is for the second part of the beam. And also these are the equations for the slope of the beam. One is between x is for x between 0 to L minus A, and the other one for x between L minus A to L. Now in this problem also we had to calculate the maximum slope and the maximum deflection of the beam. Now in order to calculate the maximum slope and maximum deflection, if you look at these two terms or expressions for the slope and deflection for x greater than 0 and L minus A, what you notice is that both of them are having terms of x. So if x is 0 here, the slope is 0. I'm sorry, the deflection is 0, and also the slope is 0. Now as you keep on increasing the values of x, the value of the deflection and slope will keep on increasing. So this will give the maximum value of slope and deflection for x is equal to L minus A from these two equations. And if you come to these two equations, the first, if you look at the slope equation, this does not have any term x here. So that means over this length, which is for x greater than L minus A and less than L, the slope remains constant. And this slope minus P L minus A square by 2 by EI is the maximum slope for this region. So basically after L minus A, the slope remains constant, and that is the maximum slope. Now for the deflection, what you do is you can see that it's a constant term here, my plus P my L minus A whole P into L minus A cube by 6 EI minus P L minus A square by 2 EI times x. So to get the maximum deflection, what we do is we put maximum value of x that is possible in this expression. So in this case, the maximum value of x is L. So the maximum deflection will also occur at x is equal to L. So the maximum displacement and slope of the beam are obtained by putting x is equal to L in those two equations. So this is the maximum slope, which is minus P L minus A square whole square by 2 EI, and the maximum deflection is minus P L minus A whole square by 6 EI into 2L plus A. So these are the maximum deflection and maximum slope at the end B. So these are the two examples that I wanted to discuss in this lecture. Now based on our observations on these two examples, I have highlighted some points about the double integration method. And these are the points that I wanted you to keep in mind whenever you are working with double integration method. First of all, the double integration method can be used to directly obtain the slope and deflection at any point along the span of a beam from the equation of its elastic curve. So if you have the moment function of a beam along its span, you can use that moment function to calculate the slope or deflection at any point by the double integration method. However, there are some drawbacks, which as I mentioned, and I'll highlight them again. Beams with discontinuous loads will have separate moment functions applicable to individual regions of discontinuities. We saw in that second example that even though there was no moment function for the region of the beam between L minus A and L, but we had to consider a separate set of equations and find two separate constant of integration in order to be able to get the equation of the elastic curve for the entire beam. And continuity conditions must be used to evaluate integration constant in elastic curves of adjacent region. So if you recall the second example, what we did is we first found the equation of the elastic curve between x equal to 0 and equation of the elastic curve for the region ranging from 0 to L minus A, and then using that equation of the elastic curve, we obtained the slope and deflection of the beam at x equal to L minus A, and these were the boundary conditions for the equation of the elastic curve between L minus A and L. Third point that I wanted to mention is the evaluation of maximum slope and deflection from equation of elastic curve requires checking of absolute values of support. If you recall the first example that I talked about, the maximum rotation of the beam, if you just take it by obtaining the higher order derivative and equating it to 0, you may not always get the absolute maximum value of the slope or deflection. So it is also essential to keep it in mind that the slope and deflection at the supports are also considered in order to be able to calculate the absolute maximum values of these quantities. Now this method, which is the double integration method, are not applicable for calculating slope or deflection of beams under complicated loading conditions and support conditions. So if you have deformations of beams due to conditions like thermal loading or some other conditions like fabrication errors, then this method is not very much suitable for calculating the deflection or slope of the beam. And also, as I mentioned, that this elastic beam theory is applicable for members which are having significant deformation due to bending, but not any significant deformation due to axial and shear force. So the last point that I wanted to mention about this method is this is not applicable for members having significant deformations due to axial loads and shear forces. So with that, I have presented what I needed to discuss about the double integration method, and what I'll do now is I will allow you all to ask any questions that you might have, and if not, we'll just take a small break of 5 minutes and then we'll start with the Macaulay's method. So if you all have any questions, I would like to hear them now and we can discuss the concerns you all. Hello?
Sir, in the example number 1, we have mx equal to m naught 1 minus xl. Sir, I'm solving it. It's coming m naught 1 plus xl. Sir, how it is m 1 minus xl? Sir, why minus sign is there? Sir, in the example number 1, the moment.
If you look at the bending moment diagram of that beam.
Yes, sir.
This is the bending moment diagram of that beam, right? So this is the x. And at x is equal to 0, the value of the moment is m0, right? And the equation I got is x is equal to m0 1 minus x over L, right?
Yes, sir.
At x is equal to L, the value of the moment is 0. If you put x is equal to L here, you get 1. So 1 minus 1, that makes it equal to 0. Now you are saying it is m0 1 plus xl.
Yes.
That is the case. Then at x is equal to L, if you put x equal to L here, you will get 2m0. So it is basically reducing. It's a negative. So that's why you should have the negative here.
Okay.
Is that clear?
Yes, sir. Yes. Sir, I got the answer. Thank you, sir.
Thank you. Okay, I got another question through the chat which says why we assume the beam is linearly elastic. Now the reason we do this is because if we do not assume the beam to be linearly elastic, then the equation that we started with, which is d2v dx square is equal to m by ei, that e term is not a constant. So if you do not assume the beam to be linearly elastic, the beam would, that equation that we are basically using as the basis of our method is not applicable. So that is the main reason why this method is applicable for linearly elastic materials or beams which are linearly elastic. Okay, there's another question that I got which is asking me how to find slope and deflection for continuous beams. Now, Before I started this lecture today, I mentioned that this is for statically determinate beams. So if you have a continuous beam which is statically determinate, all you have to do is, if you have a support which is somewhere in between the span, you basically apply the support conditions at that point into the equation of the elastic curve to evaluate the constant of integration. So if it is a statically determinate beam which is continuous, then all you have to do is the point at which the boundary condition is imposed, you apply the boundary condition into the equation of the elastic curve, and you should be able to solve for the deflection and slope of that beam even though it is continuous. Now if it is statically indeterminate, then there are other methods which have to be used, and that is not included in the scope of this talk. Okay, so if you don't have any further questions, I think what I'll do is I'll continue with the lectures, and so we'll now talk about the Macaulay's method, which is a special case of the double integration method, but it is applicable it is rather useful for beams which have discontinuities in their loading, like the one we discussed in example 2 under the double integration method. So this double integration method for beams with discontinuities in moment function can be simplified using the Macaulay's method. And what we do in Macaulay's method is we used some functions which are called singularity functions. And I'll quickly discuss what is the singularity function that we use. So the singularity functions that are used to represent the moment function with discontinuities are basically helping us to represent the entire moment function of the beam with discontinuous loading by a single equation. Now, in order to define the singularity functions, if you look at the screen, it tells you that if you have a singularity function like this, which is x minus a to the power n, now when they have this enclosed in this box brackets, this is called a singularity function. Now, how do you define this? It is for values of n, that is the exponential when it is greater than, I'm sorry, there's a typing error in this slide. Instead of a, this should be 0. So when n is greater than 0, the value of this singularity function is equal to 0 for x less than a. And when x is greater than a, the value of the singularity function is just like the normal curved bracket. So it is x minus a to the power n. Now when n, again this is an error, this should have been n less than 0, not a. So for when n is less than a, the value of this function is equal to 0 for x not equal to a, and when x is equal to a, it is undefined. Now, since if we use these functions in double integration methods, we'll be integrating and differentiating these functions a lot. It is effective to first see the integration and differentiation formulas of these functions. So if you have an integration of a step function x minus a to the power n, so for n greater than 0, it is x minus a to the power n plus 1 by n plus 1. So just like as if it is within the round brackets. However, if n is less than 0, it is just equal to x minus a to the power n plus 1. Now this is again in the box brackets. Now for the derivative, if you take d dx of x minus a to the power n, it is n x minus a to the power n minus 1 for n greater than 1. And for n less than 1, you don't have this n, it is just x minus a to the power n minus 1. Now again, notice that when you are integrating this and you are differentiating this, these box brackets remain. So that means these are still the singularity functions. Now we'll see the advantage of these properties of the singularity functions very quickly when we go to the example which is on the next slide. So this is the basic principle of Macaulay's method, where you apply this singularity function in order to represent the moment function of beams with discontinuous loadings by a single equation. Instead of using separate equations for each region having continuous loading, we'll use these singularity functions to represent the equations of the beam by a single equation. So as an example for this method, what I have done is I have taken this beam, which is, if you look at this, you can see that it is supported here at A and D. So this is a free body diagram of the beam, and it has a concentrated load at this point B, and a uniform load of 450 Newton per meter between points C and D. Now, for your convenience, what I have done is I have calculated the reactions. So I'm sure that with simple equations of statics, you should be able to arrive at these reactions. That is, at the left end, the reaction is 480 newtons, and at the right end, the reaction is 920 newtons. Now, if you want to write the moment function for these beams, now they have loadings, or rather load discontinuities at point B and C. So what happens is between A and B, there is one equation for the moment function. So for x between 0 to 2 meters, the moment function is given by this reaction 480 times x. For this region between B and C, that is for x greater than 2 and less than 3, the moment function is given as minus x is the 480x minus 500, that is 480x minus 500x minus 2. So that concentrated load, which is at a distance of 2, it comes into the picture here for the moment equation between B and C. Now, if you look at the third region, that is between C and D, the moment function is given as 480x minus 500x minus 2 minus 450 by 2 x minus 3 whole square. So now in this region, even the uniformly distributed load of 450 Newton per meter comes into the picture. So now you see that if you want to solve this by the regular double integration method, you will have 3 different sets of moment equation. You will have 6 constant of integration that you have to evaluate in order to be able to obtain the elastic curve of this beam. So now what we'll do is we'll see how we can solve it much easily using the step or singularity functions by the Macaulay's method. Yeah, this is the equation of that beam. Second order equation of the elastic curve of the beam can be written in a single equation using the singularity functions as shown below. So instead of, if you go back, so for this region it is 480x, but for this region it is minus 500x minus 2. Now if you put this in the box brackets, or if you rather use singularity functions, then you can use this second term in the same equation. Similarly, if you put this x minus 3 in the within the box bracket, that means when x is less than 3, this term becomes 0. When x is greater than 3, then only then it is applicable. So that is what we do here. We use the singularity functions to express the moment equation of that beam, and then we put it in the second order equation of the elastic curve. So EI d2v dx, this should have been v dx square is equal to 480x minus 500x minus 2. This is a singularity function, minus 450 by 2 into x minus 3 whole square. Again, this is a singularity function. Now, if you look at the properties of integration of singularity function, and if you double integrate on both sides, you will get EI d2y d, again this should have been v d2v dx dv dx is equal to 240 x square minus 250 x minus 2 whole square. So now notice, if you integrate this singularity function, you get x minus 2 whole square by 2. So that 2 is cancelling this 250, you get the 2 is cancelling this 500, so you get 250. Same thing here, 450 by 2 x minus 3 whole cube by 3, so that 3 and 2 in the denominator, they cancel this out and you get 75. So this is the first order equation of the elastic curve. EI d2v dv dx is equal to 240 x square minus 250 x minus 2 square within this singularity function, and minus 75 x minus 3 cube, plus again like we do in the double integration method, we also have a constant of integration C1 here. Again, if you integrate the both sides of this equation, you will get EI, again this will be v 80x cube. So here you integrate this, you get x cube by 3, so that 3 will cancel the 240, you will get 80. Again, the singularity function, you can integrate it, it will be x minus 2 whole cube by 3, so you get 250 by 3. This one, x minus 3 whole fourth by 4, so you get 75 by 4, and now you have the second constant of integration, which is C2. So this is the equation of the elastic curve of the beam using the singularity function, and now you see instead of using 3 different equations, we have only one equation to represent the elastic curve of the whole beam. So all that we are doing is introducing two singularity functions here. One is applicable for x greater than 2 and the other one is applicable for x less than 3. So when x is less than 2, this is not applicable. When x is less than 3, this is not applicable. So now what we have to do is solve for these constant of integration. So if you solve for this constant of integration, we'll have to look at the boundary conditions. Now this beam had restraints at the two ends. So we say that at those two ends, the deflection is 0. So at x equal to 0, the slope is 0. So that if you put x equal to 0 on the right hand side here, all these terms will become 0, and put v is equal to 0 here, you get C2 is equal to 0. And the second condition is at x is equal to L, in this case the L is 5 meters, v is equal to 0. So put x equal to 5 here, so it will be 80 times 5 cube. Now here if you put 5, 5 is greater than 2, so this term will be present. So it will be 250 by 3, 5 minus 2 whole cube. Again here 5 is greater than 3, so it will be 75 by 4, 5 minus 3 whole to the power 4 plus C1 into 5, and C2 we got it as 0 here. So that will give you the value of C1 as, again there is a mistake here, it is minus 1490. So the value of this constant is minus 1490. So C2 is 0 and C1 is minus 1490. So next thing you do, just like in double integration method, you put these values back into this equation. So if you put these values back here, this is what you will get. EI dv dx is equal to 240 x square minus 250 x minus 2 whole square minus 75 x minus 3 cube. Again, these are singularity functions, just keep it in mind. Again, there's a typing error here. This should be minus 1490. Similarly, the equation for this deflection is given by EI v 80 x cube minus 250 by 3 x minus 2 whole cube minus 75 by 4 x minus 3 fourth minus 1490 by x. So as you see that this is the equation of the slope and the deflection of the beam. Now up to here what you have noticed is the advantage of the Macaulay's method. Now what I will now show you is there are some things that even cannot be overcome even if you use Macaulay's method, and that is if you are told to calculate the maximum deflection of this beam. Now can you take this equation and equate it to 0, and that will that give you a value of the location at which this deflection is maximum? The answer is no. What you have to do is, just like you do it in double integration method, you have to consider 3 separate equations. So which I'll now show you. 80 x cube minus 250 by 3, the singularity function of x minus 2 whole cube minus 75 by 4, singularity function of x minus 3 to the power 4 minus 1490. So this is the equation of the elastic curve using the singularity function. Now if I want to calculate the maximum deflection of that beam, I can say dv dx, which is equal to 1 by EI this will become 240 x square minus 250 x minus 2 whole square minus 75 3 to the power 4 I'm sorry, there should be an x here, C1x minus 1490. Now if you straight away equate this to 0, what happens to these singularity? You cannot just ignore it or take it for calculating the values of x. So what we have to do is, just like in double integration method, we have to separate it for 3 different regions. So for x between 0 to 2 meters, the dv dx will be 1 by EI 240 240x square minus 1490. Now this you equate to 0 to get the location of the maximum deflection. If you equate this to 0, you will get x is equal to 2.49 meters. Now, if you notice that this part of that equation that I wrote here is valid for x between 0 to 2. So, and you are getting, by solving this, you are getting x is equal to 2.49. So, it is not applicable at x is equal to 2.49. So, the maximum value of the deflection cannot be obtained at x is equal to 2.49. Or in other words, the maximum value of the deflection does not occur between x equal to 0, between x equal to 0 and x equal to 2. So now what we do is we take the second equation. So for x between 2 meters and 3 meters, here dv dx can be written as 1 by EI 240x square. Now the second term, this term will come into the picture, minus 250. Now since x is greater than 2, then you can just write it using the round bracket. So x minus 2 whole square minus 1490. This term is still not applicable. It is only applicable for x is greater than 3. So but right now x is between 2 and 3. Now if you put this to 0, then you will get a quadratic equation. If you expand the x minus 2 whole square and rewrite it, you will get 1 by EI minus 10x square plus 1000x minus 2490 is equal to 0. Now if you solve this, you will basically end up with two values of x. This is a quadratic equation. So if you solve this equation, you will end up with two values of x. Now I have just solved it for your convenience. So to solve this, you will get x is equal to 2.55 meters and 99.5 meters. Now again, this value is not applicable because for this equation, the limits of application are between x is equal to 2 and x is equal to 3. This first solution that we got, x is equal to 2.55 meter, is between 2 and 3. So this solution of x is applicable in this equation. So what you do now is to calculate the maximum value of v, you put x is equal to 2.55 meters and you put x equal to 2.55 here, 2.55 here, and you solve it, you will end up with minus 2487 by EI. So from this you can see that this is one of the maximum value of the deflection. Now again, here you are getting a negative value. So what does that tell you? That tells you that that maximum deflection is in the downward direction. Now this is the second set of equation. Now there will be another third set of equation which will be valid for x greater than 3 less than 5, and for that the equation will be dv dx is equal to 1 by EI (240 x square minus 250 x minus 2 whole square minus 75 x minus 3 equal to the power 4 minus 1490. So now notice that even this singularity function at x equal to 2 and the singularity function at x equal to 3, both of them are coming into the equation and both of them have been replaced by round brackets. So this, if you equate to 0, this is a cubic equation. I'm sorry, this should be a cubic equation. So this is a cubic equation. So if you solve this, you will get three values of x. And again, if the values of x that you will get here are minus 0.36 meters, 2.54 meter and 6.68 meter. Now notice that none of these values minus 0.36 plus 2.54 and 6.68, none of them are applicable, or none of them are within this limit of x greater than 3 and less than 5. So from this we can tell you that the maximum deflection of the beam does not occur in this region between 3 and 5. So the only region where it occurs is at x is equal to 2.55 meters, and the maximum value of the slope is 2487 meters. So this is one example that I wanted to discuss with you all and show some limitations of one of the limitations. So even if you are able to obtain the equation of the elastic curve, that is the slope equation and the deflection equation by solving a single equation, but if you have to calculate the maximum slope or the maximum deflection of the beam using this method, then what you will have to do is again consider the separate equations which are applicable for each region of continuous loading, just like you do in the double integration method. So these are some of the highlights of the Macaulay's method. First of all, it is used to directly obtain the equation of the elastic curve of a beam with discontinuous loads by using a single moment equation with singularity functions. So just like you saw in the example, if you had solved that example number 3 using a direct integration method, you would have solved 3 different sets of equation and 6 constant of integration. But because you solved it using Macaulay's method, you just had to solve only one equation and 2 constant of integration. So it is definitely more convenient for calculating slope or deflection at any point over the span of a beam with discontinuous loads. However, evaluation of maximum slope or deflection from equation of the elastic curve requires consideration of separate equations without singularity functions. So if you had looked at that example that I showed, and if I showed you how to calculate the maximum deflection of that beam, for that again you have to consider the 3 separate regions. One is between x, for x between 0 to 2, the other one between 2 to 3, and the last one was for 3 to 5. Now again, just like the double integration method, this is not applicable for calculating slope or deflection of beams with complicated loading and support conditions, and also it is not applicable for members having significant deformations due to axial and shear forces. So that is all I had to present about the Macaulay's method. Now if you all have any questions about Macaulay's method, I would like to take them right now. Okay, I got a question here which I was asking, which method is feasible to find slope and deflections for nonlinear elastic and inelastic structures? Now, if you are dealing with the nonlinear elastic and inelastic structures, this method, this direct integration method, may not be applicable or may not be convenient to use. The best option I can think of is if you use some finite element analysis, that might be helpful for solving slope and deflection of structures with inelastic components. When there is STAAD.Pro, why are we using these traditional methods? Which one is more accurate? Okay, now this is a good question. When there is STAAD.Pro, why are we using these traditional methods? This is just to make you all familiar about the theories, that because if you get a software, it is always convenient to use, but at the same time, it is also important for you to be familiar with the theoretical knowledge that has been used to develop these softwares. Otherwise, if you make some mistakes while using a software, it will be very difficult for you to figure out or come out with the reason why you are making the mistake. So using a software is always welcome and it is always encouraged. You should be familiar with different kinds of software, but at the same time, you should be familiar with the basics that are behind the softwares. And if you are not familiar with those basics, then you might be using the software as a black box. And which one, regarding the second question, which is here, which one is more accurate? Now, the ones that I have discussed right now, if you're asking between direct integration and Macaulay's method, you might have noticed that they are based on the same principles. So I wouldn't say one is more accurate than the others. Now, if you are asking between energy methods and elastic beam theory methods, then I would say definitely the energy methods would be more accurate because they consider shear deformation as well as axial deformation in addition to bending deformation. What is the significance of the singularity function? The significance of the singularity function is the fact that it allows you to combine moment functions at points of load discontinuities. If you do not use these singularity functions, then you will be basically following a much more elaborate or much more complicated or much more lengthy procedure of solving this beam curve equations using the double integration method. So the main significance of the singularity function would be to combine the moment function of the beam at points of load discontinuity and thereby allow the use of these functions in the double integration method by a single function. If a moment is acting at support, how to use Macaulay's method to find slope and deflection? If there is a moment acting at the support, all you have to do first is find the moment function of the beam. If you look at the example, so if you remember the first example that I talked about where I had a moment acting at the support. So this, if you draw the moment diagram of that beam, this is also the moment function is continuous. There is no discontinuity. So in this case, I would say you don't even need Macaulay's method if I'm getting the question right. So you just find the moment function or the moment equation of the moment over the length of the beam and then directly use it in the double integration method. You don't need to use Macaulay's method for this beam. Okay, the next question I got is why Macaulay's method cannot be used for member deformation due to axial force and shear load. Now, the basic principle between Macaulay's method or double integration method is the elastic beam theory, which basically considers the deformation of members due to bending moment, and they do not consider the deformation of members due to axial force and shear load. So that is the reason why Macaulay's method or double integration method cannot be used for calculating member deformation due to axial load and shear forces. The next question I have is, can we predict directly the approximate place of maximum deflection without undergoing all those individual sections? I'm not sure if you're asking about the example that I have discussed. If it is about the example 3 that I was talking about, yes, we can look at the beam and we can definitely say that the maximum deflection of that beam would be somewhere near that concentrated load, but to find the exact location and to find the value of that maximum deflection, we definitely need to go through the exercise that I have shown where you take the first derivative and equate it to 0 and then find the location and again put the location back in the equation of the elastic curve and get the maximum deflection. How to calculate the deflection and slope using Macaulay's method for uniformly varying load? Now, if you write the moment function of a beam with a uniformly varying load, what you will notice is that there is actually no discontinuity in the moment function. So basically, you do not need to use Macaulay's method for solving a beam with a uniformly varying load. You can directly do it by using the double integration method. Whether we can use Macaulay's method for internal hinge problems, I would rather avoid using the Macaulay's method for internal hinge problems because there is a discontinuity in the slope of beam at the internal hinge. So I would rather go for double integration methods or some other method for solving the deflections using for internal hinge problems. What is the main difference between double integration method and Macaulay's method? Macaulay's method is a special case of double integration method for beams which have discontinuous loads or discontinuity in their moment function. So there is no difference in the basic principle of double integration method or Macaulay's method, but Macaulay's method is a special case of double integration method. If you all do not have any further questions, this is all I had to discuss for today, or else we'll have the next session on Friday, and there we'll be talking about the moment area theorems and conjugate beam method, which are two more methods based on the elastic beam theories of calculating deflections. Okay, so these are some of the assignment problems that I gave for this lecture. The first one that you see here is a double integration method problem. What I have here is a beam which has a roller support at one end, and it has a support at end B which is fixed, but it is not restrained in the vertical direction. There are rollers by which that beam can move in the vertical direction at end B. Now, in order to solve this, I won't be doing the detailed solution of this problem. So if this beam is subjected to a uniformly distributed load omega 0, uh, there is no discontinuity in loading, so we can easily use the double integration method. So if you write the equation of the moment function, the first thing is to find the moment function. Now, in order to solve the moment function, first of all, you should be able to draw the free body diagram. So if you draw the free body diagram, you'll get a reaction here, and a moment. Now this is omega 0, this is the length of the beam. So if you apply the equation of static equilibrium to this beam and say summation of vertical forces on that beam is equal to 0, you will be able to solve for the reaction, which will be equal to omega L, and the moment would be equal to omega 0 L square by 2. Now, to solve this beam using double integration method, what you have to do is you have to write the moment function. Now for that, it will be r into x minus omega 0 L square, I'm sorry, omega 0 x square by 2. So this is the moment function that you have to use. Now you do the double integration, so you write d2v dx square is equal to mx. In this case, it is omega 0 L x minus omega 0 x square by 2. Now you can do the double integration method, use the double integration method, you will get the expression. Now again, what we have missed here is 1 by EI. So if you solve for this, you will get some expression in x, and you will get two constant of integration, C1 and C2. Now, how do you solve for C1 and C2? What are the boundary conditions in this beam? In this beam, the boundary condition would be at x is equal to 0, the V is equal to 0, because you see it's a roller support at the left end. And the second boundary condition would be at x is equal to 0. I'm sorry, that x is equal to L, the slope of the beam would be 0. If you look at this beam, here it can move vertically, but it is fixed into this rod. So because of that, it will not have any rotation at this end. So it will be dV dL is equal to 0. So once you get these two boundary conditions, you applied it into the equation of the elastic curve, you will be able to calculate these two constant of integration, and thereby you will be able to get the equation of the elastic curve. So this is the first problem of the assignment. So that was the first problem that I just discussed. Now there is the second problem, if you see there in the assignment. This is also answering the question at which one of you all had. Determine the deflection at midpoint of the simply supported beam using Macaulay's method. So you have uniformly increasing load. So from 0, it is going to W up at the center of the beam, and then it is again decreasing. So the question that somebody asked me is, what do we do if we have a uniformly increasing load? So this is the uniformly increasing load. First thing you have to do is calculate the reaction. So here, if the length is L, So the total load on the beam is half omega times L. So the reaction at each of these supports would be omega L by 4. Okay, to write the equation of the moment function, it will be omega L by 4 x minus omega by L by 2 into x. So that is, if you take it at a distance x, this value is omega by L by 2 into x. So this into half into x into 1/3 x. So this is the equation for x between 0 to L by 2. Now if it has increased continuously up to the entire span of the beam, this would have been applicable for the whole beam. So that basically answers the question. So if it has been an uniformly increasing load, then this equation would have been valid for the entire beam. Now since there is a change in the slope of the loading, so from uniformly increasing, it is going to uniformly decreasing here. So because of this, we have to use the Macaulay's function. Now, how do we apply Macaulay's function? So what we do is, we first assume that this uniformly increasing load is over the entire span. So for that, this equation will be applicable for the entire range of the beam. However, over this region of the beam between L by 2 and L, we assume that there is a load which is acting in the upward direction. So basically, the summation of these two load is equal to this. So if I draw it again, this loading can be considered to be equivalent to this loading minus or you can say plus and then apply this load in the upward direction. So this is L by 2, this is L by 2 and this is L, this is L. So if this is W here, at midpoint it is W, so here it is 2W. So this is also W. So now if you want to write the moment function of this beam, what do you get? For this, there will be one reaction here, R1. This is R2. For this case, it will have reactions R1 dash, R2 dash. So the total reaction would be R1 plus R1 dash. Now that R1 plus R1 dash would be equal to the reaction due to this loading, which is omega L by 4. So if you want to write the moment equation for this beam, it will be omega L by 4x minus half 2 omega by L x into x by 3 plus, you have to consider this part. So this is 2w by L by 2, or here it will be x minus L by 2 into x minus L by 2 into x minus L by 2 by 3. Now this term is only applicable for the portion of the beam between L by 2 and L. So what we do is, you can use the singularity function for that part, which is omega L by 4 x minus half into 2 omega by L x x into x by 3 plus 2 omega by L by 2 into, now this is where the singularity function is coming into the picture, cube by 3. So this is the one equation that you can use to represent the moment function of the entire beam. Now here the discontinuity in loading is the change in the direction of increment of the uniformly varying load. Here it was increasing, here it was decreasing. Had it been increasing overall over the entire span of this beam, then you would not have needed this singularity function. Only this much, the first and the second term, would have defined the moment function of the beam. So because we have the increase in the slope, or I'm sorry, a change in the slope of the uniformly, because we have a change in the slope of the uniformly changing load of the beam, that is why we are bringing in this last term here, which has a singularity function. So now once you have the moment equation of this beam using that singularity function, and it is a single equation, the rest of the steps is similar to what I have shown. You write d2v is equal to d2v dx square is equal to mx over ei, and then you perform double integration. You perform double integration and you would be able to solve this. Now again, if you perform double integration, you will be coming up with two constants of integration. So this will give you v is equal to some terms in expressions in x plus c1x plus c2. So these are the two constant of integration, and you will be again using the boundary conditions. So in this case, for the beam, the boundary condition would be at x equal to 0, the deflection would be 0, v is 0. At x is equal to L, again deflection is 0, v is equal to 0. So these are the two boundary conditions you will be using to solve this beam. So once again, since you have the moment function using the singularity equation using the singularity function, the rest of the procedure should be easy to solve. So once again, I encourage you to solve this assignment problem as well, which is on the Macaulay's method. So these two problems, the first and the second problem that you have in the assignment, you should be able to solve it after today's lecture. So the first one you have to solve by the double integration method, and I have just given you some hints about how to solve, what are the boundary conditions you have to use. Second one is by Macaulay's method, and once you are able to write the moment function of the beam using the singularity function, you should be able to solve it, because here the boundary conditions are also simple. So if you have any doubts about any of these two problems, you can now ask me, and otherwise I once again request you to solve these two problems after the class today. Okay, I have a question. What is the problem with complicated loads and supports? What are the methods available to find deflection in complicated beam? What is theory behind softwares that are available to find deflections in complicated loads or beams? Now, the first question that you have is, what is the problem with complicated loads and supports? Now, when I said complicated loads and supports, I basically meant beams which have loadings due to other factors like thermal loads. Now, because of these thermal loadings, what will happen is you do not have the elastic beam theory applicable for these beams. So because of that, you cannot use these methods for solving the beams using the elastic beam theory for complicated loads. Now, what are the methods? The last method, that is the energy method that I will be covering in this topic, they can be used to some extent to find deflections due to these thermal loads or due to fabrication errors. What is the theory behind softwares that are available to find deflections in complicated loads? Now, different commercial softwares have different theories. Energy methods is one of the theories that is used to solve for deflections due to thermal loadings or fabrication errors. There might be other methods which are applicable. So it is always advisable to basically go through the manuals of these softwares and check for the methods. And always most of the softwares have a technical help that is available, and they should also be referred to when you are in doubt about the theories or the methods that are being followed at the background of these softwares. Okay, this is a good question. Somebody is asking me how to determine if the deflection is small or large. Uh, there are several ways. So what you see is this will become more clear when we study the energy methods. But for the timing, I will tell you that there are different ratios between the shear span and the depth of the member, which there are guidelines. So normally, if you go for design codes, they will tell you now how do you determine if deflection is small or large. For example, if the theory of the elastic beam theory behind these methods, that is the elastic beam theory, if you find that the deflection is not small enough, and if you calculate the rotation at any point and you find that it is not much smaller than 1, then I would say that it is not small enough to be neglected. So if you want to find like a numerical value, I would suggest one of the ways is to calculate deflection or rotation and see if how much it is less than 1. And now if you find that value to be comparable to 1, I would say that then you cannot apply this uniform, the elastic beam theory like the way we did. Which is the easiest method for general use? Now there is no one method which can be said to be the one easiest for all problems. So it depends on the problem. For example, if you get a beam which is having no load discontinuity, I would say double integration method. If you have a beam which has load discontinuity, then it becomes Macaulay's method. Now, it again depends from problem to problem. So the way to find out by looking at a problem and deciding which method is easy is something that you have to gain through experience. The more you solve problems, the more experienced you will be in order to judge which method should be used for a particular problem. Okay, we still have 5 more minutes. If you have any questions, you can ask. Otherwise, we'll meet on Friday to discuss the next 2 methods, which is the moment area theorem and the conjugate beam method. Okay, I got one more question. When a point load acts on a beam, the shear force diagram changes its point or contraflexure in a vertical manner, but in StatPro, the diagram shows slope. Okay, the next question I got is, can we use double integration method for analysis if the beam will have different I values? Yes, you can. So what will happen is, again, you will have, instead of load discontinuity, there will be a discontinuity in the I. So for each region of the beam with a different value of I, you will write one different equation. And again, you will have to use the continuity conditions at the intersection of these 2 regions to solve the constant of integration. So yes, it can be used for solving beams with different values of I. Under what circumstances we can prefer Macaulay's method? Under any circumstances where there is a discontinuity in the M by EI expression, you are welcome to use the Macaulay's method, provided you can formulate the moment function or any other changes that are occurring or causing the discontinuity. Okay, I'll try to take that question one more time. When a point load acts on a beam, the shear force diagram changes its point of contraflexure in a vertical manner, but in StatPro, the diagram shows slope. Which SFD is correct? Okay, so are you asking, if you are asking me why there is an inclination in the shear force diagram at the point where you are applying the load, I think it is something to do with the graphics that the software is using. But you are right, when in theory, whenever there is a concentrated load, the shear force diagram basically either goes up or goes down, and depending on the load. And so the value of the shear force is different basically to the left and right of the point of load application. Maybe to depict that, the softwares might have a graphical interface which basically shows the change over a small length in a magnified manner, and that is why you see the slope of in the shear force diagram, even though actually it is a instantaneous change from one value to the other. Okay, the another question is, under what I think I just answered this. Under what circumstances we can prefer Macaulay's method? As I said, any circumstance where there is a discontinuity in the m by ei function, you should be trying to use the Macaulay's method using, provided you can formulate the m by ei equation using the step function. Is there any special method or procedure to solve vertical beam? The the elastic beam theory that I explained was for a horizontal beam, but if you just rotate the axis, it becomes vertical, and so it should be able to use this method for beams which are vertical. Okay, so I think the time is up, so we'll stop the discussion today. And if you all still have any more questions for this topics that I covered today, I'll take it at the beginning of the next session on Friday. And otherwise, I'll go ahead with the next two topics, which is moment area theorem and conjugate beam methods on Friday. Thank you. you.